Good morning, chemistry students. Here is your teaching video for Chapter 9, Day 1. Your notes, we're going to do all of Chapter 9, Section 1, including the chem math. So this chapter is about stoichiometry. In my opinion, this is probably one of the most important chapters, especially for those of you who are going to go to college and have to take a college chemistry class. Most college chemistry classes are going to have a lab component, and pretty much every single time you do a lab, you will do these stoichiometry calculations. So basically what we're going to be doing in this chapter is we're going to be taking your ability to write and balance chemical equations and add math to those balanced chemical equations. So add those 5 conversion factors that you learned back in Chapter 7. So a great thing for you to have out and available while you're taking notes over all throughout Chapter 9 is to have your periodic table out with your helper sheet, and to have your chemistry toolkit, that index card you made back in Chapter 9, out and available as well, so that you can look at those tools that you have. So this is called stoichiometry, and this first section is about the arithmetic of equations, and we're going to be talking about using everyday equations. And so we're going to start by defining what stoichiometry is. And stoichiometry is the calculation of quantities in chemical reactions. So you are definitely also going to need a calculator. You need to be able to put scientific notation in your calculator, okay? But we will be doing a lot of calculations, a lot of math throughout this chapter. Now, these calculations themselves are actually called stoichiometric calculations. And these are calculations using balanced equations. So that's why in the previous chapter you learned how to write and balance chemical equations, because you need to have a properly written and balanced chemical equation to be able to do stoichiometric calculations. You can think of stoichiometry and these stoichiometric calculations as a chemist's form of bookkeeping. So this is how chemists know that how much reactants they need to produce a certain amount of product. And you often do this in cooking. In fact, probably if you've made cookies before, you might have actually done some stoichiometric calculations. So again, you have probably made a stoichiometric calculation when you've been baking cookies. So let's take a look at an example of that. I'm going to bring in a picture here real quick. And it's kind of hard to read. Actually, let's cut that. Let's put it on this one. Okay, I know it's a little hard to read, but again, if we're making cookies, right, this recipe we see calls for, it's peanut butter cookies, which is one of my favorite, and it calls for 3/4 of a cup of creamy peanut butter, a half a cup of Crisco, 1 1/4 cups firmly packed light brown sugar, 3 tablespoons of milk, a tablespoon of vanilla, a large egg, 1 3/4 cups of flour, 3/4 of a teaspoon of baking soda, and 3/4 of a teaspoon of salt. So you've probably done a stoichiometric calculation before. This recipe says it makes 3 dozen. Let's say that you're supposed to bake cookies for all your teachers, and you have 5 teachers, and just let's say you also want a dozen for yourself. So you're making each of your teachers a dozen cookies and a dozen for yourself. So you need 6 dozen cookies. What would you do to this recipe? You wouldn't follow this recipe the way it is, right? You would double this recipe. And so you would double the amounts of everything that you need. That's a stoichiometric calculation. Okay? Because you want to produce twice as much, you know that you need to double the recipe. Let's say you went to make these cookies and you discovered that you only have, okay, like a 1/4 cup of peanut butter instead of 3/4 of a cup. Well, you would have to take this whole recipe and divide it by 3. That's a stoichiometric calculation. So you have done these before with cookies, and probably if you've done some baking before, where you've adjusted your recipe to figure out how much you want. Chemists do this all the time. This is definitely the kind of math that a chemist who's working at a chemical company would do on a regular basis. Because again, if you have an order for a certain amount of pharmaceutical drug, right? If you have an order for 1,000 pounds of it by some company, right? You don't want to produce 5,000 pounds of it. That's way too much. But you also can't only produce 500 pounds of it because that's not enough. And so a chemist would do some stoichiometric calculations to figure out how much of our reactants do we need to start with so that we produce the amount of product we're supposed to produce. So this is definitely the type of calculation that for those of you that are going to continue and take a college level chemistry class that you will likely do at some point in the future. So stoichiometric calculations require balanced chemical equations. So we want to kind of review what kind of information we can get from a balanced equation. And we're going to look at an example. So we're going to look at the sentence that nitrogen gas reacts with hydrogen gas to produce or to yield ammonia gas. So, for stoichiometric calculations, the first thing you always need is a properly balanced chemical equation. So nitrogen gas would be N2, right, because it's part of Dr. Brinkelhoff. Hydrogen gas is H2, also because it's part of Dr. Brinkelhoff. And ammonia is NH3, and it's also a gas. Again, I'm not real particular about states of matter, but they had them here, so we'll include them. Now, we need this to be a balanced chemical equation. So I have 2 nitrogens, so I'm going to put a coefficient of 2 in front of ammonia. And I have 2 hydrogens here, and I have 6 hydrogens in ammonia, so I need a coefficient of 3 in front of hydrogen. And now my equation is properly balanced. So now, using this specific balanced chemical equation, let's talk about what information we can actually get from it. One of the types of information we can get from all balanced chemical equations is our number of particles. Now, the particles we're talking about depends on the substance. If we're talking about an element, our particles will be an atom. If we're talking about a molecular compound, our particles will be molecules. And if we're talking about an ionic compound, our particles will be formula units. So particles is just kind of generic. Now, in this example, all of these are molecular compounds, so I would interpret all of these specifically in terms of molecules. And in terms of particles, I can interpret this way. I have one molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. So to interpret it in terms of particles, I'm going to use my coefficients, and those coefficients tell the relative numbers of particles. So again, had I had an element here, then I wouldn't say molecule, I would say an atom. If I had an ionic compound here, I wouldn't say a molecule or an atom, I'd say a formula unit. But the coefficients tell me the relative numbers of particles, so I just use the coefficient to interpret a balanced chemical equation in terms of particles. The second set of information that we can get from this balanced chemical equation, which again, I'll just put up here so that we have it to look at. We can interpret this balanced chemical equation in terms of moles. In terms of moles, I would interpret this example as 1 mole of nitrogen plus 3 moles of hydrogen produce 2 moles of ammonia. So again, to interpret a balanced chemical equation in terms of moles, the coefficients on our balanced chemical equations indicate the relative numbers of moles. So we just use the coefficients that we have to interpret our balanced chemical equation in terms of moles. So that's the second piece of information we can get from our balanced chemical equation. Again, I'm going to put my balanced chemical equation up here so I have it to look at. The third piece of information we can get from our balanced chemical equation is we can interpret this balanced chemical equation in terms of mass. Now, we know that our balanced chemical equations must follow the law of conservation of mass. Remember, we've been using the law of conservation of mass when we balance our chemical equations, but the law of conservation of mass also says that the mass of our reactants has to equal the mass of our products. Now, again, we use this idea when we balance chemical equations and we counted our number of atoms because the mass of an atom doesn't change. So if I have the same number of all of the different types of atoms on both sides of the equation, then I am going to follow the law of conservation of mass. But we're going to prove this a little bit right now. So we're going to actually do some math right now. So you're going to need your your periodic table, okay, and a calculator potentially. So again, if I use those moles, I have 1 mole of nitrogen. And I'm going to use a tool off of my chemistry toolkit called molar mass to convert moles of nitrogen to grams of nitrogen to see how many grams that is. Now again, in molar mass, it's always a 1 in front of moles. And for nitrogen, I'm going to make this easy and I'm just going to use whole numbers. So nitrogen's molar mass on the periodic table is 14.007. But there's 2 nitrogens, so it's going to be 14 times 2, which is 28 grams. So I get 28 grams of nitrogen. All right, how much hydrogen? Again, I'm going to start with my coefficient, so I have 3 moles of hydrogen. Again, I'm going to use the molar mass of hydrogen, so 1 mole of hydrogen is how many grams of hydrogen. And again, to get the number that goes here, I use my periodic table. Hydrogen's mass is 1.0079, and there's 2 of them, so this is going to be 2. So 3 times 2 is 6 grams of hydrogen gas. So that's the mass of my reactants. I need to figure out the mass of my product. So I have 2 moles of ammonia, again using my coefficient on my balanced chemical equation. 1 mole of ammonia, again I'm going to use the molar mass for ammonia to figure out how many grams of ammonia I have. So again, nitrogen was 14. And each hydrogen is 1, so that makes a mass of 17. Okay? And 17 times 2 is 34. Now, according to the law of conservation of mass, the mass of my reactants should equal the mass of my product. 28 plus 6 equals 34 grams of my reactants. And I only have 1 product, and I have 34 grams. So I proved the law of conservation of mass here. So on your homework at some point, you have some questions like this, and this is the type of work that you should show for it. So again, so far I can interpret my balanced chemical equation in terms of particles. To interpret it in terms of particles, my coefficients are equal to my relative numbers of particles. I can interpret my balanced chemical equation in terms of moles. Again, when I interpret in terms of moles, my coefficients are equal to my relative numbers of moles. I can interpret my balanced chemical equation in terms of mass. It has to follow the law of conservation of mass, and so the mass of my reactants has to equal the mass of my products. The last way I can kind of interpret my balanced chemical equation or information that I can get is about volume. And again, our equation here is N2 plus 3H2 yields 2 ammonias. So volume, remember we have to be talking about it being at standard temperature and pressure. But then it tells us about the moles of gases. So again, how would I interpret this in terms of volume? Again, here's an example. So again, I'm going to use those coefficients. So my coefficient says I have 1 mole of nitrogen. And I know that at STP, 1 mole of nitrogen has a volume of 22.4 liters. Oops, should be a 4. Again, that's a tool. It's the molar volume tool off of your tool kit. So I have 22.4 liters of nitrogen gas at STP. Okay, for hydrogen, I have 3 moles of hydrogen gas. And again, I know because of molar volume that 1 mole of hydrogen gas occupies a volume of 22.4 liters at STP. So, 22.4 times 3 gives me 67.2 liters of hydrogen gas. Lastly, I have 2 moles of ammonia. And again, when I have ammonia gas at STP, I know that 1 mole of ammonia gas occupies a volume of 22.4 liters. So 22.4 times 2 gives me 44.8 liters of ammonia gas. Now notice there is no conservation law about volume, okay? But again, on your homework at some point on a test or quiz, you have a question where it asks you to interpret your chemical equation in terms of volume, and this is what I would like to see. So again, 4 pieces of information that we get from our balanced chemical equation. We get particles using our coefficients. We get moles using our coefficients. We get mass. To interpret an equation in terms of mass, we have to use molar masses and do some math. And we get volume. And again, to interpret our equation in terms of volume, we have to assume we're at standard temperature and pressure, and we have to use our molar volume and do some math. So this is the information we can get from these balanced chemical equations. We kind of already did this a little bit, but we want to do a review of your conversion factors. And again, remember, these should always all be on your chemistry toolkit from back in Chapter 7. I asked you to use an index card to put the 5 tools, the 5 conversion factors that we were using, okay, throughout that chapter. We're going to continue to use those chemistry toolkit and those conversion factors throughout this chapter as well. So it's very important that you know where that index card is, and if you don't know where it is, that you create a new one with the information we're going to review right now. So remember, when we learned about moles, we learned that a mole can be used for 3 different things: for counting, for mass or weight, and for volume. And for each of those, there's a tool, at least one tool, on your chemistry toolkit. So the mole can be used for count. We tend to refer to this one as Avogadro's number. And our count one was that we have 6.022 times 10 to the 23rd representative particles over 1 mole of our substance. This was the generic one, and so you might not actually have written this one on your chemistry toolkit. Okay, so this was generic. Remember, the power of these is depending upon where I need my unit to be, I can flip this. So I could write it as 1 mole of substance over 6.022 times 10 to the 23rd representative particles. Where the units go depends upon where you need the units to be, so they cross out in your calculations. So we have talked about 3 different substances. We've talked about an element. We've talked about a molecular compound. And again, we know it's a molecular compound because it's made of 2 nonmetals. And we've talked about an ionic compound. And again, we know a substance is an ionic compound because it's made of a metal and a nonmetal, or it contains a polyatomic ion. So what is that representative particle? What is that smallest piece of these substances that if I have a big chunk of it, I chop it up into and it still has all the original properties of the substance? That smallest piece of an element is called an atom. That smallest piece of a molecular compound is called a molecule. And again, remember, we're abbreviating that MOLC. And that smallest piece of an ionic compound is a formula unit, which is usually everybody's favorite abbreviation because we call it an FU. For mass, these are all just molar mass. We can find the molar mass of any of these. All we have to do is add up the masses of the elements that are in it using the masses from our periodic table. So many of you didn't have just one on here. You had 3 tools on here. You had a tool that related to the element. So you had 1 mole of element is 6.022 times 10 to the 23rd atoms. Okay, and again, I can flip this depending upon where I need it to be. Okay, you had 1 for molecular compounds. You had that 1 mole of molecular compound is Avogadro's number. Molecules. And again, depending upon where I need my units to be, I can flip this. And lastly, you had 1 for ionic compound. You had the 6.022 times 10 to the 23rd. Formula units was 1 mole of ionic compound. So most of you didn't have this generic one. Most of you had these 3 specific ones. And again, the advantage of these is that I can flip them depending upon where I need my units to be. That's the advantage of all conversion factors. So you should have these 3 tools on your chemistry toolkit. We will use them some, probably not as much in this chapter as we did back in chapter 7. The second way we can use our mole is for mass or weight. Again, the name for this tool is molar mass. And our conversion factor for molar mass is our number of grams of our substance over 1 mole of our substance. And again, or depending upon where I need my units to be, it could be 1 mole of a substance over my number of grams of my substance. Now, where do I get my number from? My number comes from adding my masses on the periodic table. Now, it seems to me that some of you are kind of struggling with this a little bit. So we're going to write a chemical formula and figure out its molar mass. We're going to do iron 3 sulfate. So again, I need to write the chemical formula. Sulfate's a polyatomic ion you have memorized, so this is an ionic compound, so I'm going to write symbols, charges, crisscross, lowest whole number ratio. My symbol for iron is Fe. It has a charge of +3, that's what the Roman numeral is telling me. Sulfate you have memorized is SO4. It has a charge of -2. And I'm going to crisscross those down, so I'm going to end up with Fe2, SO4 in parentheses, a 3. Now, you do not have to show your work, but I'm going to show my work here just to help you remember how to do these. So in this compound, I have iron, I have sulfur, and I have oxygen. I have 2 irons because of the subscript of 2. Okay. I have 3 sulfurs, and I have 12 oxygens. So for sulfur, I have 3, and for oxygen, I have 12. Then I'm going to use my masses from my periodic table. I'm just going to go ahead and use 1 decimal place. Remember, when you're doing it, you're going to want to use however many significant figures you have in your problem. Iron's mass is 55.845, so I'm going to say it's 55.8. Sulfur's mass from my periodic table is 32.065, so I'm going to say it's 32.1. And oxygen's mass is 15.999, so I'm going to say it's 16.0. Okay, so then again, I'm going to do 2 times by 55.8, and I get 111.6. I'm going to do 3 times by 32.1, so I get 96.3. And I'm going to do 12 times by 16. So I'm going to get 192.0 here. And then I'm going to add all of those up. So plus my 96.3 plus my 111.6. And I get a mass for iron 3 sulfate of 399.9 grams per mole. So that is a review. Now again, you don't have to show this work. Never are you required to show this work. Okay? I showed it here so that you could kind of remember how you calculated your molar masses of compounds. So, again, we can use our mole to talk about a count. It can be used for counting. And for counting, our conversion factors are going to include Avogadro's number. We can use our mole for mass or weight. When we use our mole for mass or weight, we're going to use molar mass as our conversion factor. Our last way that we can use the mole is for volume. And again, when we use our mole for volume, we're going to be talking about molar volume. And to use molar volume, we have to be at standard temperature and pressure, right, which we call STP. So to use our molar volume, we have to be at STP, and our molar volume is 22.4 liters of gas over 1 mole of gas. And again, or depending upon where I need my units to be, 1 mole of gas over 22.4 liters of gas. So you should have, okay, a total of 5 tools on your chemistry toolkit. Here's tool number 1. And again, most of you didn't probably write it both ways. Here's tool number 2, molar mass. And then here's tool number 3, 4, and 5. Okay, so make sure that you have those tools on your chemistry toolkit because you're going to continue to use them throughout this unit and throughout Chapter 9 as we do stoichiometry and stoichiometric calculations. So, A little more review. Remember, for our dimensional analysis, which we talked about back in Chapter 3, dimensional analysis, also sometimes referred to as the factor label method, okay, is used to convert between units to do dimensional analysis problems. We use conversion factors. Conversion factors are a ratio of equivalent or equal measurements all of these circled in red. These are conversion factors. Okay, so molar volume is a conversion factor. Molar mass is a conversion factor. These three tools with Avogadro's number in them, they are conversion factors. They are equivalent measurements or equivalent amounts. The advantage of using conversion factors is that conversion factors are equal to 1. So it's like multiplying something by 1. And you use them so your units cancel out. And the purpose of a conversion factor is that it's used to prevent mistakes. So it allows you to verify that you have the correct units that you're expecting to have your answer in before you do your calculation. Now, you did learn the metric system, and I don't think you'll have to use it a whole lot, but remember back in Chapter 3, you also had this mega, kilo, hecto, deca, base, deci, centi, milli, micro, nano, pico. And remember, this is where our metric system is large, and this is where our metric system is small. Okay? And remember, these lines in here are factors of 10 that you have to include. You won't use the metric system a whole lot throughout our stoichiometric calculations, but just a reminder that you have used it previously. So that brings us to the end of these notes. Your homework assignment is on page 241, questions 6 through 8. These are going to be problems. Do not type them. I want your problems handwritten because you have to show me all your work. Like these that we did back here, you have to show me this type of work. That's a pain in the butt to type. Do not type it. Handwrite it out on a sheet of paper and use the Adobe Scan app or take a picture of it to turn it in for your assignment. Have a great day. I'll talk to you tomorrow.